In this video, we're going to learn how to solve optimization problems using calculus. I'll show you the step-by-step process for setting up and solving these types of problems, then walk you through 8 examples so you'll know exactly what to do when you're asked to find a maximum or a minimum value. Be sure to download the free guided notes to follow along and work through the examples with me. Let's start by going over the main steps that you need to follow when solving an optimization problem. The first step is to read the problem carefully and identify what the problem is asking you to find. The second step is to organize the information into 4 categories. The first category is diagram and variables. You need to draw a picture, if possible, and label all the quantities. The second category is the equation that relates the variables that you wrote down in the first category. The third category is the quantity that you are going to maximize or minimize, and you need to express this in terms of one variable. And then the last category is the domain. This is important because you need to know the possible values for the variable. The third step is to differentiate the quantity that you're going to maximize or minimize, find the critical points, and then evaluate the function at those points to find the possible maximum or minimum value. The fourth step is to justify your answer. How you complete this step will depend on whether the domain is open or the domain is closed. We'll walk through examples of both of these so that you'll know exactly what to do. The last step is to use the maximum or minimum value to answer the question. Let's now walk through 8 examples. These are the most common types of optimization problems that you'll probably see. In this optimization problem, we're going to find 2 numbers whose product is as small as possible. The first step in solving this problem is to read through the problem carefully and figure out what information we have and what we're asked to find. In this problem, we are to find 2 numbers whose difference is 100 and whose product is a minimum. The second step is to fill in all 4 of these categories using the information from our problem. Since we need to find 2 numbers, let's let x be our first number. And then let's let y be our second number. Now let's think about the equation that relates these 2 numbers. Our problem tells us that the difference between these 2 numbers is 100. So we can write down that x minus y is equal to 100. Now let's see if we need to find a minimum or a maximum. Our problem states that the product is a minimum, so I'm going to highlight minimum, and let's write down an equation for the product. The product is just the 2 numbers multiplied, so this is going to be x times y. Now what we need to do is we need to put our product in terms of just one variable, and we're going to put it in terms of x. So that means we need to go back to our equation and solve our equation for y. So from this equation, we see that y is equal to x minus 100. Now we can plug that in for our product p. So p is equal to x times x minus 100. In the next step, we will need to find the derivative of p. So what we need to do now is we need to rewrite p in the best way that makes the derivative as easiest as possible. I'm going to write this as p is equal to x squared minus 100x. That way we won't have to use the product rule. I'm going to highlight our product because we're going to need to refer back to that. Now let's think about the domain. We are given no constraints on our numbers, so our domain is going to be that x can be anything from minus infinity to infinity, and this is an open domain, and I'm just going to write that down because we're going to need that in just a few minutes. Our third step is to take the derivative of our product and then find the critical numbers. Let's go ahead and write down our product. P is x squared minus 100x. Now let's find the derivative. P prime is 2x minus 100. To find the critical numbers, we are going to set that equal to 0, and we get that x is equal to 100 divided by 2, so we find that x is equal to 50. Let's go ahead and let's highlight that. Now we can go ahead and find y. Y is equal to x minus 100, so y is equal to 50 minus 100, which gives us that y is equal to minus 50. And let's highlight that. Now that we know x and y, let's find our minimum value. P is x squared minus 100x, but it's also equal to just xy, and that's going to be easier. So we're going to write it like that. X is 50, y is minus 50. So this gives us that P is equal to minus 2,500. And we'll highlight that. Now it may seem that we're done, but we're not. We have 2 more steps that we need to complete. We need, in step 4, to justify that our product is a minimum. To do that, because we have an open interval, we need to use the first derivative test or the second derivative test. Our derivative, highlighted up here in blue, is relatively simple. So I think using the second derivative test will be the easiest. So let's do that. P double prime is equal to 2, and that is greater than 0. This means that our function is concave up, and we have a minimum. So let's write down that we have a min at x is equal to 50, and then that tells us that P is equal to minus 2,500 is a minimum value. Now our last step is to reread our problem and clearly state our final answer in a complete sentence. Let's go back up. Our problem tells us that we need to find 2 numbers. So that's the question that we need to answer. So we're going to say that the 2 numbers are 50 and minus 50. And that's our final answer. In this optimization problem, we're finding the dimensions of a rectangle with a fixed area that has the smallest possible perimeter. The first step in solving this problem is to read through the problem carefully and figure out what information we're given and what we're asked to find. We want to find the dimensions of a rectangle with area 8,000 meters squared, whose perimeter is as small as possible. The second step that we're going to do is we're going to fill in these 4 categories using the information from our problem. I already went ahead and wrote down our diagram, which is a rectangle. Now we have to put variables with our rectangle. I'm going to let this length be x and this be y. Now we need to identify these variables. So we're going to say that x is the length, and then y is the width. Now what we need to do is we need to find an equation that relates these 2 variables. We are told that the area is 8,000 meters squared. So the equation needs to be an equation for the area. So we're going to write down that A is equal to xy, and that is equal to 8,000 meters squared. Now let's determine if we're going to find a maximum or a minimum. Our problem tells us that our perimeter needs to be as small as possible. So that means that we are going to minimize the perimeter. Let's write down the equation for the perimeter. The perimeter is all four sides, so it is going to be 2x plus 2y. Now what we need to do is we need to write our equation for our perimeter in terms of one variable. I want to write it in terms of x, so we need to find an equation for y in terms of x. We're going to get that from this equation right here, and we can say that y is equal to 8,000 divided by x. So let's go ahead and let's put that in. P is 2x plus 2 times 8,000 divided by x. Since we need to minimize p, we need to take its derivative. So at this stage, what we need to do is we need to write p in the easiest form possible to take a derivative. So I'm going to write p as 2x plus 16,000 x to the minus 1. Now let's think about our domain. We are given no constraints on our length x, but we know that a length can't be negative, and it also can't be 0 if we have an area of 8,000. So let's write down that x has to be greater than 0, and our domain is open. We'll need that in a few minutes. In our third step, we're going to take the derivative of the quantity that we are going to minimize. So I'm going to go ahead and let's highlight this. That's what we need to take the derivative of. Let's go ahead and let's copy it down. P is 2x plus 16,000 x to the minus 1. Now we can take the derivative. P prime is equal to 2 minus 16,000 x to the minus 2. We need to set this equal to 0, so let's go ahead and let's simplify this first. This is 2 minus 16,000, all divided by x squared. And now we can get a common denominator. That's x squared. So we have 2x squared minus 16,000 in our numerator. I'm going to go ahead and highlight this because we're going to need this in a little bit. Now what we're going to do is find our critical values. So we're going to take our derivative and set it equal to 0. This gives us 2x squared minus 16,000 is equal to 0. I want to make a note that x is in our denominator and could be a critical value at 0, but our function is not defined at 0, so it's not going to be a critical value. So we're just going to look at where the numerator is equal to 0. So this gives us 2x squared is equal to 16,000. And this gives us x squared is equal to 8,000. Now we're going to take the square root. X is the square root of 8,000. We can pull out 100 from this, and the square root of 100 is 10, so we can write this as 10 times the square root of 80. And then let's think, 4 goes into 80, so we can pull out a 2. So this is 20 times the square root of 20. And then the square root of 20 is 4 times 5, and we can pull out another 2. So our x is going to be 20 times 2, which is 40, times the square root of 5. And now let's put units on it. We are working in meters. So we found that x is equal to 40 root 5 meters. Now let's go ahead and solve for y. I'm going to do that over here. Y, let's go back up to the top, is 8,000 divided by x. So y is equal to 8,000 all divided by 40 root 5. 40 goes into 8,000 200 times, so we have 200 divided by root 5. And now let's go ahead and let's get rid of the root 5 from the denominator. So what we're going to do is we're going to multiply by root 5 and divide by root 5. So we're going to get a 5 in the denominator. 5 goes into 240. So we end up, let me erase our equal sign here and put an arrow. So we end up with y is equal to 40 root 5 meters. And let's go ahead and highlight that. Notice that x and y are the same. So let's just make a note that our rectangle is a square. Now, it may feel that we're done, but we're not done yet. What we need to do is we need to find the minimum perimeter. So let's go ahead and let's solve for p. Our p is given up above as 2x plus 16,000 x to the minus 1, but it's also written up above as 2x plus 2y. So I'm going to use that form because it's easier. Our perimeter then is 2 times x, which is 40 root 5, plus 2 times y, which is also 40 root 5. So we end up with, let's see, 80 plus 80 gives us 160 root 5, and then we put in a unit of meters. And let's go ahead and let's highlight that. In step 4, we need to justify that our answer gives a minimum value. Because our domain is open and our derivative, let's see, I highlighted that in blue, that derivative is pretty complicated. So I think we should use the first derivative test instead of the second derivative test to justify that p is a minimum. So let's write this down. We're going to use the first derivative test. And I'm just going to put p prime here because we're going to need that. P prime is equal to 2x squared minus 16,000 all divided by x squared. To do our first derivative test, I'm going to put a number line, and this is going to be x. Let's indicate that x starts at 0 but is not equal to 0. And let's go ahead and put our critical point on here, which is 40 square root of 5. Now what we have to do is find the value of p prime to the left and right of this point. All we need to do is find if it's positive or negative. So let's go back over here to our derivative, and I'm going to highlight just the numerator. The denominator has a squared term, so it's positive, so we don't need to really worry about that. 40 root 5 is where what I've highlighted in orange is equal to 0. So that means that to the left of 40 root 5, p prime is going to be negative, and it's going to be positive to the right. Now let's think of this in terms of increasing and decreasing. If p prime is negative, our function is decreasing, and then it's increasing, and that tells us that we have a min. So I'm going to write down that we have a min at x is equal to 40 root 5, and p is equal to 160 root 5 meters is a minimum. And let's highlight that. Now we're almost done. Our fifth step is to reread the problem and carefully state our final answer in a complete sentence. Let's go back up to the top. Our problem says that we are to find the dimensions of the rectangle, and our dimensions are length and width. So let's write down that the length is 40 root 5 meters. We always want to make sure and include units in our answer. And the width is also 40 root 5 meters. And we'll highlight this because that is our final answer. In this optimization problem, we're finding the largest possible volume of a box with a square base and an open top. The first step in solving this problem is to read through the problem carefully and figure out what information we're given and what we're asked to find. We're told that if 1,200 centimeters squared of material is available to make a box with a square base and an open top, we want to find the largest possible volume of the box. The second step is to fill in each of these 4 categories using the information from our problem. I went ahead and drew a box with a square base. Now what we have to do is label the sides. If it has a square base, this length and this length can both be X, and then we'll let this height be Y. So let's write down that X is our length and our width. You always want to write down what the variables are. And then Y is our height. Now let's write down our equation. Our equation is going to relate the variables from our diagram to the information that we're given. So let's look back up. In our problem, it says that we have 1,200 centimeters squared of material. So that means the base, the sides, and the top has to equal 1,200 centimeters squared. So let's write down that we have a surface area of 1,200 centimeters squared. And then let's also write down what our surface area is. It's equal to the base, which is x squared. And then it's equal to all 4 sides. And those 4 sides are the same. So we're just going to have 4xy. So our equation is going to be x squared plus 4xy is equal to 1,200. We'll leave out the units for right now. Now let's go ahead and find if we are going to maximize or minimize a quantity. Going back up to the problem, it says we are to find the largest possible volume. That means that we're going to maximize the volume. So let's write down what the volume is. The volume of our box is the length times the width times the height. So that is x squared times y. Now we need to put our volume in terms of one variable. So we need to come back to our original equation right here, and we need to solve for y. So let's go ahead and let's do that. We have 4xy is 1,200 minus x squared, and that gives y is equal to 1,200 minus x squared, all divided by 4x. Now let's take that and put it back up into our equation for v. So we have x squared times 1,200 minus x squared, all divided by 4x. Looks like one of the x's is going to cancel. So we end up with 1/4 x times 1,200 minus x squared. Let's go ahead and let's multiply this through. So we have our v is equal to 300x minus 1/4 x cubed. And we are going to need that, so I'm going to go ahead and highlight that. Now let's think about our domain. We are not told how big the length and the width of our box can be, but we do know that it can't be 0 and it can't be negative. So we're going to say that our domain is x is greater than 0, and let's just make a note that this is an open domain. We'll need that in just a few minutes. Our third step is to take the derivative of our volume and find its critical points. I'm going to go ahead and rewrite our equation for our volume. It is 300x minus 1/4 x cubed. Now let's go ahead and let's take the derivative. Our derivative is 300 minus 3/4 x squared, and we're going to set that equal to 0. So we have 300 is equal to 3/4 x squared. If we multiply by 4 and divide by 3, we are going to get, let's see, 1200 divided by 3 is equal to x squared. So this tells us that x squared is 400. And we take the square root of that, and it's really nice. And we get that x is equal to 20. Now we need to put units. Let's go back up. We have centimeters squared for surface area, so x is 20 centimeters. And we'll go ahead and highlight that. Now we need to find y. Our equation for y is right here. So let's use that. Y is equal to 1200 minus x, which is now 20. So we have 20 squared, all divided by 4 times 20. Let's see. This is 1200 minus 400. So this is 800 divided by 80. So we get that y is equal to 10 centimeters. Now what we need to do is find our maximum volume. So let's write down our equation for V. Let's see, we can pick two of them. V is x squared y right here, or the one we have below that. Let's use the x squared y. That one's going to be easier. So V is x squared times y. X is 20, so this is 20 centimeters squared. Y is 10 centimeters. So let's see, this is 400 times 10, so this gives us 4,000 centimeters cubed. Now, it may seem that we're done, but we're not. Our next step is to justify that the answer that we got is a maximum. Our interval is an open interval, so we can use the first derivative test or the second derivative test. Let me go ahead and let's highlight our derivative. There's our derivative right there. That derivative is pretty easy, so I think it's going to be easiest to use the second derivative test. So let's write that down. We're going to use the second derivative test. It would not be wrong to use the first derivative test. It would just be a little bit harder. And let me go ahead and write down here what our first derivative is, so we can then take the second derivative. Let's go ahead and let's find v double prime. It is equal to minus 6 over 4x, which is minus 3/2 x. Now we're going to substitute in that x is equal to 20 centimeters. So we'll say v double prime at 20 is minus 3/2 times 20. And this is minus 30, and it's less than 0. We really don't care what the number is. We just need to know if it's positive or negative. Because it's negative, our function is concave down, and we have a max. We can then say that we have a max at x is equal to 20 centimeters. And then we can also say that v is equal to 4,000 centimeters cubed is a maximum. Now we just have one more step. That step is to reread the problem and then clearly state our final answer in a complete sentence. Let's go back up and look at our problem. Our problem says to find the largest possible volume. So that's what we need to state. So we're going to write down that the largest possible volume is 4,000 centimeters cubed. And that's our final answer. In this optimization problem, we're finding the least expensive way to build a rectangular storage container with a given volume. The first step in solving this problem is to read through the problem carefully and find out what we're given and what we're asked to find. We are told that a rectangular storage container is to have a volume of 10 meters cubed. We're then told that the length of its base is twice the width. Material for the base cost $10 per square meter, and then material for the sides and lid cost $6 per square meter. We are to find the cost of materials for the least expensive container. Our second step is to put all this information into the 4 categories that I have listed here. I went ahead and drew a storage container, and now we just have to label the sides. We're told that the length is twice the width. So let's let our width be x, and then our length can be 2x. And then we'll go ahead and let the height be equal to y. Now we need to go ahead and write down these labels. You always want to label your variables. X is our width. 2x is our length. And then y is our height. Now what we want to do is find an equation that relates these variables and what we're given. We are told that our container is to have a volume of 10 meters cubed. So we can say that our volume is going to be the width times the length times the height. So that's 2x squared y, and that is equal to 10 meters cubed. Now let's see if we want to maximize or minimize something. We want to find the cost of the materials for the least expensive container. So that means we are going to minimize the cost. Let's write down the equation for our cost. I think this is the hardest part of the problem. Our cost is going to include the base, and that is 2x squared. And that is $10 because the base has to be stronger. So 10 times 2x squared. And then we're going to add on to that the sides. Let's do the front and the back first. That's this piece and that piece. That is XY, and we have 2 of them. And it is $6, so we have a 6 times 2XY. Now let's do the other 2 sides, this side and that side. Those are also 6. So we have 6, and that is 2xy, but there's 2 of them. So we have 2 times 2xy. And then we have the top, that is 2x squared, but it is $6. So we have a 6 times 2x squared. Now let's go ahead and let's simplify all this. Let's look at the x squared terms first. We have 20 and 12. So that gives us 32x squared. Now let's look at the xy terms. We have 12 and 4 times 6 is 24. So 24 and 12. And that gives us 36. So we have a 36 XY. Now we need to write this just in terms of x. So what we're going to do is we're going to go back to our equation for our volume, and we're going to find out what y is. Y is going to be 10 all divided by 2x squared. So we get that y is equal to 5 over x squared. Let's go ahead and substitute that in. Our cost is 32x squared plus 36 times x. And now we have 5 over x squared for y. We want to take the derivative of this function, so I'm going to rewrite it in the easiest way that we can take the derivative. And that's going to be c is equal to 32x squared plus 36 times 5. Let's see, 30 times 5 is 150, and then 5 times 6 is 30. So this is 180, and we have an x in the denominator, so we're going to write that as x to the minus 1. And there's our equation for our cost. Now let's think about our domain. We are told that the box has no limits on the length and the width, but we do know that x can't be 0 and it can't be negative. So we're going to say that x is greater than 0 and our domain is open, and we're going to need that in a few minutes. Our third step is to take the derivative of our cost function and find the critical values. Let's go ahead and let's write down c. It is 32x squared plus 180x to the minus 1. Now we can take the derivative. C prime is 2 times 32, which is 64x, minus 180x to the minus 2. Let's go ahead and let's simplify this. This is 64x minus 180 all over x squared. So let's go ahead and let's get a common denominator of x squared. In our numerator, we then have 64x cubed minus 180. I'm going to go ahead and highlight that because we're going to need that in a minute. To find the critical values, we have to set our numerator equal to 0. We're not going to worry about our denominator because that gives us x is 0 and our cost function isn't defined at 0. So we just have that 64x cubed minus 180 is equal to 0. So this gives us x cubed is 180 divided by 64. Let's see how we can simplify this. Let's divide both the top and bottom by 2. So this is 90 over 32. And we can divide the top and bottom again by 2. So this is 45 over 16. And we can't divide that any further. So we know that x then is going to be 45 over 16 to the 1/3. And we need to go back up and look at our units. It is in terms of meters. So we're going to put meters for x. Now we can go ahead and find our cost because that's what we want to minimize. Our cost right up here is 32x squared, and that is 45 over 16. Because it's squared, we have a 2/3. And then we have plus 180, and our x is 45 over 16, and it's to the minus 1. So this is minus 1/3. Now you get to throw that in your calculator, and when you do, you get a value. I'm going to put a $sign here because it's cost. We have $191.28. And let's go ahead and let's highlight that. Now, it may seem that we're done, but we're not. We need to justify that this cost is a minimum. To do that, we need to go back up to our interval. It is open right under the domain there. So that means we can use the first derivative test or the second derivative test. I highlighted our derivative in blue. It is complicated, so I don't think we want to take the derivative of that again. So for step 4, to justify our answer, we are going to use the first derivative test. And I'm just going to recopy our derivative because that's what we're going to need. We have 64x cubed minus 180, all divided by x squared. Because the denominator is positive, all we're going to be concerned about is the numerator, because we just need to find if c prime is positive or negative to the left and right of our critical number. Let's go ahead and let's draw a number line. We'll label this as x. We'll indicate that we have an open interval starting at 0, and let's put our critical point. It is 45 over 16 to the 1/3. At our critical point, the function that I highlighted in orange is equal to 0. So to the right of that critical point, We're really just concerned about our leading term, which is x cubed, and it is positive. So we know that c prime is going to be positive in this region, and then it's going to be negative in that region. This means that our function, which is our cost function, is going to be decreasing in this region and increasing in this region. And we can see that we then have a min at x is equal to our critical point. So let's write down that we have a min at x is equal to 45 over 16 to the 1/3. And we'll write down that c is equal to $191.28 is a minimum. We'll go ahead and we'll highlight that because that's really important. And now we can go to our last step, which is just to reread the problem and clearly state our final answer in a complete sentence. Let's go back up to and look at our problem. It says, find the cost of materials for the least expensive container. So our answer needs to be that the cost of the least expensive container is $191.28. And that's our final answer. In this optimization problem, we're finding the point on a line that's closest to a given point. The first step in solving this problem is to read through our problem carefully, figure out what information we're given, and what we want to find. Our problem states that we want to find the point on the line, and that line is 6x plus y is equal to 9. That is closest to the point minus 3, 1. For step 2, we are going to fill out all 4 of these categories with all the information that we've been given from the problem. I went ahead and drew our point. This point is the point minus 3, 1. And then I drew our line, which is 6x plus y is equal to 9. We want to find a point on the line, and that's our red point here. So we're going to just label this xy. That's the point that we need to find. And it's the point that is closest to the point minus 3, 1. Let's go ahead and identify our variables. So we're going to say that x comma y is our point on the line. It's always good to write that down in words. Now what we're going to do is write down the equation that relates x and y. And that's actually the equation that we already wrote down, and it's the equation for our line, 6x plus y is equal to 9. And we'll come back to that in a minute. Let's now go to our next category and find out if we want to find a maximum or a minimum. We want to find the point on the line that is closest to the point minus 3, 1. So that means we have a distance, and I'm going to label this little d right here, between these 2 points, and that's what we actually want to minimize. So let's highlight min, and let's write down that we want to minimize d. Let me write down just the general equation for the distance between 2 points. It's the square root of y minus y1 squared plus x minus x1 squared. Now let's go ahead and let's substitute that x1 is minus 3 and y1 is 1. So this is the square root of y minus 1 quantity squared plus x plus 3 quantity squared. Now I'm going to show you a trick. I don't know if it's really a trick, but it's the easiest way to do this problem. If you want to minimize a distance, you can instead minimize a distance squared. And that's what we're going to do. We instead are going to minimize d squared, and we're going to call it capital D, and it is y minus 1 squared plus x plus 3 squared. The reason we're doing this is we're going to have to take a derivative of this function, and by getting rid of the square root, the derivative is so much easier. Now what we want to do is we want to substitute in for y, and we're going to go back to our equation for our line and use that to find y. So let's write down that y is equal to 9 minus 6x. So let's plug this in. Capital D is 9 minus 6x minus 1 quantity squared plus x plus 3 squared. This gives us 9 minus 1 is 8, so we have 8 minus 6x squared plus x plus 3 squared. The other piece of information that we need to fill in for this problem is the domain, but I'm going to hold off doing that until after we complete step 3. Now we're all set to go on to step 3. I'm going to highlight this because we're going to need that. Our third step is to find the critical values of our function capital D, so we need to take the derivative and set it equal to 0. I'm going to go ahead and recopy what we have. D is 8 minus 6x squared plus x plus 3 squared. We could have multiplied that out and found the derivative, but I think it's just as easy to do it this way. We're going to take the derivative, and we're going to need the power rule and the chain rule. So this is 2 times 8 minus 6x times the derivative of what's inside, which is minus 6, plus 2 times x plus 3. Now let's go ahead and multiply everything out. We have minus 12 times 8 minus 6x. I'm going to do that in 2 steps. Plus 2x plus 6. This gives us a minus 96 plus 72x plus 2x plus 6. And this leaves us with 74x minus 90. And I'm going to highlight that because we're going to need that in a few minutes. Now we can find the critical value. We're going to set this equal to 0. And this is going to give us that x is equal to 90 divided by 74. And we can divide both of those by 2. So we get that x is equal to 45 divided by 37. And let's highlight that. Now let's go ahead and let's find y, because we eventually want to find the point on the line. So we're going to need y. Y, let's see, we need to look back up here. Y is 9 minus 6x. So this is 9 minus 6. Oh, this is complicated. 45 over 37. Let's see here. We're going to multiply 9 by 37, and that is going to be 333. And then we subtract off 6 times 45, which is 270. And all of this gets divided by 37. So this gives us that y is equal to 63 over 37. Now what we need to do is find our minimum distance. So let's first find capital D. Capital D is 8 minus 6 times our x, which was 45 over 37. And that gets squared, plus x, which is 45 divided by 37 plus 3 quantity squared. I am not going to take time in this video to work through that calculation, but you end up with 676 all divided by 37. So that tells us that our distance little d is the square root of 676 divided by 37. And this gives us that d is 26 divided by the square root of 37. Let's go ahead and let's highlight that. That is our minimum distance. Now, it may feel that we're done, but we are not. We need to justify that this distance is a minimum. Let's go back up and fill in our domain. If we go back up to our problem, we have no constraints given on x. So that means that x can be anything. So we're going to say that minus infinity is less than x is less than infinity. And this is an open interval. So for our justification, we can use the first derivative test or the second derivative test. Our first derivative is highlighted up here in blue. It's really simple, so we definitely want to use the second derivative test. And I'm going to go ahead and write the first derivative. D prime is 74x minus 90. So D double prime is 74. That is greater than 0. This means that our function is concave up, and we have a minimum value. So let's write down that we have a min at x is equal to 45 over 37. And this tells us that our distance, little d, is equal to 26 over the square root of 37 is a minimum. And we'll highlight that. Now we are almost done. We just have to write down our final answer. To do that, we need to go back up and reread our problem and then clearly state our final answer in a sentence. We need to find the point on the line that is closest to the point minus 3, 1. So for part 5, we're going to write down that the closest point is 45 divided by 37, comma 63 divided by 37. And that's our final answer. In this optimization problem, we're finding the rectangle of largest area that can be drawn under a parabola. The first step in solving this problem is to read through the problem carefully and figure out what information we've been given and what we're asked to find. The first step in solving this problem is to read through the problem carefully and figure out what information we've been given and what we're asked to find. We want to find the dimensions of the rectangle of largest area that has its base on the x-axis and its other two vertices above the x-axis and lying on the parabola y is equal to 8 minus x squared. Step 2 in solving this problem is to fill in the 4 categories that I've listed here using the information from our problem. I went ahead and drew a rectangle that has its base on the x-axis and its other two vertices above the x-axis and lying on the parabola. What we want to do now is to put variables on our picture, and our variables need to relate to what we want to find. We want to find the dimensions of the rectangle with the largest area. The rectangle is written here in red, so that's what we want to put our variables on. I'm going to label this piece as x, and this piece as y, and then this piece as x again. Notice that we didn't label the entire base x, we broke it up into 2 pieces. And the reason that we did that is the point xy is this point right here, and it lies on the parabola. And if we let x be the entire base, we couldn't identify that point as xy. Notice that x can be as big as this point right here, so I think we should go ahead and label that point. That point is where our parabola, 8 minus x squared, is equal to 0. So that point is x squared is equal to 8, which gives us x is equal to the square root of 8, or 2 square root of 2. Let's now label our variables. 2x is the width of our rectangle, and then y is the height. You always want to label the variables. Now let's write down the equation that relates these variables. That equation was actually already given to us, and that is the equation y is equal to 8 minus x squared. Now let's look up at the problem again and see what we want to maximize or minimize. We want to find the dimensions of the rectangle of largest area. So that means we want to maximize the area of the rectangle. So let's write down the formula for that area. A is equal to the length, which is 2x, times the height, which is y. So our area is 2xy. Now what we want to do is put our area in terms of just one variable. So we're going to let this y equal that y. This gives us A is equal to 2x times 8 minus x squared. In order to maximize our area, we are going to have to take the derivative of A. So what's really good to do is to go ahead and rewrite A in the easiest way that we can take the derivative. I'm going to write A as 2 times 8, which is 16, so 16x minus 2x cubed. And let's highlight that because that's the area that we're going to take the derivative of in a few minutes. The last thing we need to fill in is the domain. X can range from 0 all the way up to 2 root 2. So we're going to write this as 0 is less than or equal to x is less than or equal to 2 root 2. And this is a closed domain, so I'm just going to write down closed. That is going to matter to us in just a few minutes. Our third step is to take the derivative of our area function, set it equal to 0, and find the critical values. I'm going to rewrite A. A is 16x minus 2x cubed. Our derivative, A prime, is 16 minus 2 times 3 is 6x squared. And we are going to set that equal to 0 and solve for x. This gives us x squared is equal to 16 divided by 6. Now we're going to take the square root. So x is the square root of 16 divided by 6. So we can say that x is equal to 4 divided by the square root of 6. Let's go ahead and let's highlight this. And then notice that our base is equal to 2x. So I'm just going to make a note over here that 2x is equal to 8 divided by square root of 6. Let's now find what y is equal to. Y, if we go back and look up top, is 8 minus x squared. So this is equal to 8 minus 16 over 6. This is 48 minus 16, all divided by 6. And that is 32 divided by 6. So we can say that y is equal to 16 divided by 3. What we want to do now is find what our area is equal to. Our area, going back up to the top, is 2xy. We could have used the formula for area that I just wrote down by step 3, but that one's actually harder. So let's use the formulation 2xy, and let's plug in x and y. So our area is 2 times x, which is 4 divided by root 6, and then y is 16 divided by 3. This is equal to 128, all divided by 3 times root 6. And let's go ahead and let's highlight that answer. Now, it may feel that we're done, but we're not. What we have to do now in step 4 is we need to justify that this answer that we just got is a maximum. Since our domain up here is a closed interval, the way we have to justify this is compare the value of our area at our endpoints to that of our critical point and just see if the one at the critical point is our biggest one. A at 0 is equal to 2xy when x is 0. So this is just equal to 0. And then a at 2 root 2 is equal to 2 times 2 root 2. And then let's go back up here. At this point right here, y is 0. So we can plug in 0 for y. And we get 0. And then we have a at our critical point, which was 4 over root 6. And we found that that value was 128, all divided by 3 root 6. And that is bigger than 0, so that is our maximum. Now, our last step is to reread our problem and then clearly state our answer in a complete sentence. Let's go back up to the top and look at our problem. We are asked to find the dimensions of the rectangle. So that's what we need to put in our answer. We can say that the width of the rectangle is 4 divided by root 6, and the height is 16 divided by 3. And there's our final answer. In this optimization problem, we're finding the largest rectangle that can fit inside a right triangle. The first thing we want to do in solving this problem is to read the problem carefully, figure out what information we've been given, and then what we're asked to find. Our problem tells us that we are to find the area of the largest rectangle that can be inscribed in a right triangle with legs of length 3 centimeters and 4 centimeters if two sides of the rectangle lie along the legs. What we want to do now is fill in all 4 of these categories that I've listed here. And notice that I have already drawn our picture just to make things easier. We have a right triangle, and inscribed in our right triangle is a rectangle, and it has legs of length 3 centimeters. So this distance here is 3 centimeters and 4 centimeters. So this distance here is 4 centimeters. Now what we want to do is assign variables. Our variables need to be related to what we want to find. We want to find the area of our rectangle here in red. So we need to make our variables the width and height of our rectangle. So I'm going to let this distance be x and this be y. So let's write that down. X is the width of our rectangle, and then y is the height of our rectangle. Our second category is titled equation. What we need to do for this is we need to find an equation that relates x to y. I think this one is difficult, and a lot of students struggle with this. So let me tell you exactly how we're going to do this. To find the equation that relates x and y, we're going to use similar triangles. If you've studied related rates, you might remember doing this when you had water going into a cone. Now what we're going to do is we're going to compare the sides of our 2 triangles. So let me go ahead and let me highlight our second triangle. This right here is our second triangle, and it has a leg of x. And then this distance right here is 3 minus y. So using similar triangles, we can say that 3 is to 4 as 3 minus y is to x. Let's put that in our pocket for a minute and we'll come back to it. Let's now move on to what we want to maximize or minimize. We want to find the area of the largest rectangle. So that means that we are going to maximize the area of the rectangle. So we need to write down the formula for that area. The formula for the area of our rectangle is x times y. And now we need to get this formula for a just in terms of x. So we're going to go back to our equation and we're going to solve this for y. Let's go ahead and let's cross multiply. This gives us 3x is equal to 12 minus 4y. So we can say that 4y is equal to 12 minus 3x, and y is equal to 12 minus 3x, all divided by 4. Let's now go ahead and substitute that in for our area. A is now x times 12 minus 3x, all divided by 4. What we're going to do in step 3 is to take the derivative of a so that we can find its critical values. And it makes it easier to take the derivative if we write a in the simplest form possible. So I'm going to rewrite this, and I'm going to say that a is equal to 12 over 4, which is 3. So we have 3x minus 3/4 x squared. Then we can take the derivative easily without having to use the product rule. The last category that we have to fill out is the domain. Let's go back here and look at our diagram. The domain is in terms of x, and x can be between this point and this point. So we can say that x is between 0 and 4, and this is a closed interval. So I'm going to put that down because that's going to make a difference to us in a few minutes. For step 3, we want to take the derivative of our area function and find its critical values, and then find the maximum value of a. So let's go ahead and let's rewrite a. A is 3x minus 3/4 x squared. Now we can go ahead and take the derivative. A prime is equal to 3 minus 6 over 4 times x, and we're going to set that equal to 0. So we have 3 is equal to 6 over 4 times x. So this means that 12 over 6 is equal to x. So we can say that x is equal to 2, and we need units with this. So let's go back up. And notice that in our original problem, our links are in terms of centimeters. I guess we did write that down on the diagram. So x is equal to 2 centimeters. Now let's go ahead and let's find y. Here's our equation for y, and that's what we're going to use. So let's say that y is 12 minus 3 times 2, all divided by 4. This is 12 minus 6, which is 6 divided by 4. We can say then that y is equal to 3/2, or 1.5 centimeters. Now what we need to do is find our maximum area. And we have two equations for the area. Let's go back up here and look. We have this equation and this equation. They're the same thing. I think a is equal to xy is going to be a lot easier to use. So let's use that to find what a is. So we'll write down a is x times y. X was 2 centimeters, so this is 2 centimeters. And then y was 3/2 centimeters. So we get that our area is 3 centimeters squared. It may now feel like we're done, but we're not quite done. What we have to do now is justify that this area that we got is a maximum. And to do that, we have to go back to our domain and see if it's open or closed. This domain is closed, so that means that to justify that our area is a maximum, we have to find A at our endpoints and then compare it to the 3 centimeters squared. To find our area at the endpoints, let's go back up and look at our diagram. At this point on our left, x is equal to 0, and then at this point on our right, y is equal to 0. We know that our area is equal to x times y, and we can use that. So A at 0 is going to be 0 because x is 0, and then A at 4 is going to be 0 because y is 0. And then we have A at our critical point, which is 2 centimeters, is equal to 3 centimeters squared. So this is our maximum area. Now we're almost done. Our last step is to reread our problem and clearly state our final answer in a complete sentence. Let's go back up to our problem. We want to find the area of the largest rectangle. So we have to state what the area is. Let's state that the area of the largest rectangle is 3 centimeters squared. And that's our final answer. In this optimization problem, we're designing a poster with margins that allow the printed area to be as large as possible. I think this is one of the hardest optimization problems to do. I'm going to explain things really clearly so that by the end, you will know exactly how to solve this type of problem. The first thing we want to do to solve this problem is to read through the problem carefully and figure out what information we're given and then what we're asked to find. We are told that a poster is to have an area of 180 inches squared with 1-inch margins at the bottom and sides and a 2-inch margin at the top. I went ahead and drew a picture of this just so that you can see what that looks like. We're asked, what are the dimensions of the poster that will give the largest printed area? Our second step is to fill in this chart that I've listed, and we'll start with the one on the left, the diagram and variables. We want to find eventually the dimensions of the poster. That's going to clue us in that we need to make the width of the poster equal to a variable x and the height of the poster equal to a variable y. Let's write that down. X is the width of the poster, and then y is the height of the poster. Now let's go ahead and let's put our margins into our picture. Up in yellow, I have highlighted that we have 1-inch margins at the bottom and the sides. So let's just mark that this is 1 inch. This is 1 inch. We'll squish it in there. And then this is 1 inch. And then our top margin is 2 inches. Now what we want to do is we want to write down an equation that relates our diagram to other information that we've been given. We are told that the poster is to have an area of 180 inches squared. So we can say that our area of our poster is x times y, and that is 180 inches squared. Now let's go over and figure out what we want to maximize or minimize. We want to find the largest printed area. The printed area is the part inside here, and I'm going to label that as PA. So that's what we want to maximize. So let's write down that we want to maximize our printed area PA. Now what we have to do is get an equation for PA. Let's do the width first. This width here is going to be x minus 2 because we have 1-inch margins on each side. And then this height is going to be y minus 3 because we have a 2-inch margin at the top and 1 inch at the bottom. We can then say that our printed area PA is equal to our width, which is x minus 2, times our height, which is y minus 3. Now, we are going to take the derivative of the printed area so that we can maximize it. And we only want to do this if it's in terms of one variable. So let's go back to our equation and let's solve our equation for y and plug it in right here. Y is equal to 180 divided by x. Let's now put that in. PA is equal to x minus 2 times 180 divided by x minus 3. We have to take the derivative of this, and I think it's going to be complicated to find if we leave our printed area in that form. So let's go ahead and let's use the FOIL method and multiply these two quantities. Our printed area, and let me write FOIL up here because that'll help us, FOIL. The first terms are x times 180 divided by x, so that's just 180. And then we're going to multiply the outer terms, and that gives us a minus 3x. And then our inner terms give us a minus 360 over x. And then our last terms are plus 6. And we can rewrite this and combine the 180 and the 6. So we have 186 minus 3x minus 360. And then let's write this as x to the minus 1 because it'll be easier to take the derivative. I'm going to highlight this because we are going to need to be able to go back up and find this. Let's now think about our domain. We are not given any constraints on how big or small the poster can be. We do know, however, that x can't be 0 or less than 0. So let's write our domain is x is greater than 0, and this is an open domain. We're going to need to know that when we go to justify our answer. Our third step is to take the derivative of our printed area function, find the critical values, and then find the maximum value. Let me go ahead and let's write down our printed area function again. This is 186 minus 3x minus 360x to the minus 1. And now let's go ahead and take the derivative. I'm going to write this as PA prime, and this is minus 3 plus 360 x to the minus 2. We are going to need to set this equal to 0, so let's simplify it. This is minus 3 plus 360 all divided by x squared. Let's get a common denominator of x squared. So this gives us a minus 3x squared plus 360 in our numerator. Now we're going to set this equal to 0 to get our critical values. Notice that we could have a critical value at 0 because our denominator is equal to 0 when x is 0, but our function isn't defined at 0, so we don't have to worry about that. We just have to worry about the numerator being equal to 0. This gives us 3x squared is equal to 360. So x squared is equal to 120. And this gives us x is the square root of 120. Think of 120 as 4 times 30. So we can pull out the square root of 4 as 2. So we have x is equal to 2 square root of 30, and then we need units, so let's go back up. Everything is in terms of inches, so we can write down inches. Let's go ahead and let's highlight that. So that's x. Now we need to find y. We have an equation for y hiding somewhere. Let me go ahead and highlight it. It is right here. 180 divided by x. So let's write down that y is 180 divided by x. So this is 180 all divided by 2 root 30. This then is 90 divided by root 30. And I think we should go ahead and multiply by root 30 over root 30. This is going to make things easier. So this gives us that y is equal to 90 divided by 30, which is just 3, square root of 30. And again, we have inches for our units. Now what we have to do is find the maximum printed area. Let's go back up here. Notice that we have two equations for PA. Let me put a check by these. We have this one and this one. I think the first one, x minus 2 times y minus 3, is going to be the easiest one to use to find out what PA is. So let's write down that PA is x minus 2 times y minus 3. And now let's substitute in for x and y. X is 2 root 30. So we have 2 root 30 minus 2. And then y is 3 root 30 minus 3. Let's go ahead and use the FOIL method and multiply all of this out. Our first terms are 2 root 30 times 3 root 30. So this is 6 times 30. And then our outer terms gives us a minus 6 root 30. And then our inner terms is the same thing, minus 6 root 30. And then our last terms gives us a plus 6. So our printed area is 180 plus 6. So that is 186 minus 12 root 30. Not a nice answer. Inches squared. And we'll go ahead and let's highlight that. Now, it might feel that we're done, but we're not quite done yet. What we have to do now is we have to justify if the answer that we just got is a maximum. Let's go ahead and let's look back up here. This expression right here is our first derivative. We can use the first derivative test or the second derivative test for our justification. Honestly, I don't think it matters for this problem which one we use. I think they're both complicated. I am going to choose to use the first derivative test. So I'm just going to put down what our derivative is. PA prime is minus 3x squared plus 360 all divided by x squared. We want to find if our derivative is positive or negative to the left and right of our critical value. Because our denominator is an x squared, we really just have to look at the numerator. Let's go ahead and let's draw a number line. And we'll put x on this. We'll remind ourselves that it is an open interval starting at 0. And let's put our critical value. That is 2 root 30. To the right of our critical value, as x gets really, really large, we just have to look at the leading term. That is negative. So we know that this is going to be negative. And then if we pick a point to the left of 2 root 30, say 1, we get that our derivative is positive. This tells us that our function, which is our printed area, is increasing and then decreasing. So we do have a max at x is equal to 2 root 30 inches. And our max is equal to PA, which is our 186 minus 12 root 30 inches squared. Now, the last thing that we have to do is to reread our problem and then carefully state our final answer in a complete sentence with units. Let's go back up to the top. We want to find, up here in green, the dimensions of the poster. So let's go ahead and let's state that. Step 5, we're going to say that the width is 2 root 30 inches, and the height is 3 root 30 inches. And that's our final answer. And that's it. You've learned the complete process for solving any optimization problem, from identifying the variables and writing equations, to finding critical numbers and determining maximum and minimum values. To really master these problems, make sure to work through plenty of examples on your own.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.